Okay. Get started. Make sure you shut down your laptops and turn your silent phones and whatnot. So, let me ask if people are still having trouble with EdLab access. There is some questions about accessing the EdLab. Problems with it, figure it out. Okay. You know your username and you couldn't figure out your password, or you didn't know what your username is. What is the problem? Okay. So here is some of you or many of you are probably familiar with what the EdLab is. Accounts for your courses are created by FCFS. If you already have an account for some other class, your username and password is exactly the same. If you don't know your username or you have forgotten your password or don't know what it is, you should go to SCF during normal business hours. Okay, we can probably tell you your username because we have a list of students registered and we can figure out your username. We cannot tell you what your password is, right? I think you should go there. Okay, so if you have any problems with accessing the EdLab, and there are several questions on EdLabs, please go see SCF. If all you need to know is what your username is, and you just forgotten it or something like that, you can email the TA and tell you what. If the password resets, please go there and check with it. Okay? Quick input on how the discussion section went. Any quick comments on Friday's discussion? Generally going okay or not going? Indifferent. Okay. So, if you have any thoughts on anything with the discussion section, please let me know so we can figure out how to make that a better experience. Okay. So let's start. Excuse me. So last time we were talking about processes. I introduced the definition of what is a process. It is essentially a program in execution. It's the dynamic execution context of a process or a program rather. Processes are tracked by OS kernel using a data structure called the process control block. For every process that is active in the system, there is a process control block entry for that process that tracks everything the OS needs to know about that process, okay? Which would include the process state, memory management information, scheduling information, and open files that the process has and whatnot. Okay? We talked about process states, that they could go all the way from new, ready, waiting, running to terminated. You did some exercises in the discussion section on this. Okay. We also talked a little bit about the notion of a context switch. Okay, what is a context switch? The fact that you save the state of the currently running process. Okay, in the process control block, you pick another process for execution from the ready queue to restore its registers, and then it starts running. And all of this operations are referred to as a context switch collectively. Okay? And then towards the end, I said processes could be independent, where they have nothing to do with one another, or they could be cooperating processes, where they work together to achieve some higher level application tasks. Okay? And I said the two ways by which processes can cooperate is either through message passing, where they send messages back and forth, okay? Or through shared memory, where there is a special region of memory that's allocated and both processes can access it. And I said by default, a process's memory cannot be accessed by another process. So that's memory protection that the OS enforces. So if you wanted to share some region of memory, you couldn't just give it a pointer or some such thing, because when the other process tries to access your memory region, this first process's memory region, it's going to get a segmentation fault. So in order to share memory, you have to explicitly allocate memory to a system call and say it is a piece of memory that's going to be shared across processes. And this is referred to as shared memory in Unix systems. Okay? And then you can use that region between two or more processes to exchange information. Okay? So that is where we left off last time. what we are going to do today is look at scheduling algorithms. Okay, I will introduce what is the notion of scheduling. We'll look at several policies. We may not get through all of these today, but we'll try to get through as many of them as possible. Okay, FCFS, round robin, shortest job first, multi-level feedback queue, lottery scheduling. These are a suite of policies that an OS kernel could use to schedule processing. Typically, you pick one of these and that's what is in the kernel. And you look at what each of these gets us and what are some of the disadvantages. Okay. So let me start with a little bit of background into scheduling. Okay. First of all, the reason we need to have scheduling at all is we assume that most general purpose operating systems are multi-programmed, which means that more than one process is active in the system at any given time. Okay? And as you have already seen, these processes could be in one of these 5 different states, okay, that we know. So and each state has a queue associated with it, and the process control block entry for that process is in that queue for that state. Okay? Now in this case, we are specifically interested in the ready queue. Okay? The ready queue has a list of all the processes that are ready to run, they are ready to execute. Okay? And it's up to the kernel to decide which one is actually going to run next, okay? Which one is going to be chosen from here and actually get to execute, in which case it appears transitions to this state. Okay? And the policy for doing this is called CPU scheduling. You can pick from one of many different policies when you decide which of those processes that are queued up is actually going to get to execute. And that's what we are going to look at today. Okay, so that's the high level background. Okay, and before I go into specific policies, I want to distinguish between 2 types of scheduling. One is called long-term scheduling and the other is called short-term scheduling. Okay, long-term scheduling allows the OS to determine the degree of multi-programming. It is basically something that the OS uses to decide what is the maximum limit on the number of active processes in the system. Okay? And if the number of processes exceeds that value, it will not allow the users to start new processes. Okay? Typically, you may have never hit this limit. Okay? But rarely do you get an error message from the OS when you, let's say, try to start a browser or your mail client or whatever the application may be. Rarely would you have seen a message saying, sorry, there are too many processes in the system, try again later. Okay? But the OS is tracking internally how many processes are active, and there is a limit. It's a very high limit which most users never reach. Okay? It is very easy to reach this limit if you write a buggy process that keeps forking new child processes, which is referred to as a fork block. Okay? If you keep doing this, you'll have lots and lots of processes, and soon you will hit the long-term scheduling limit, and your application that is continuously forking processes will start getting errors. Work will start getting errors saying too many processes. Okay? But normally you will not reach that limit at all, and that's referred to as long-term scheduling. The reason it is there at all is that this limit allows the OS to ensure that all active processes can make progress. There is enough hardware resources for all of those processes, which could be tens or hundreds of processes, can all make progress in the system. If you are too many, then you're spread too thin. You do not have enough resources to allow them all to make progress. Okay, so there is an upper bound, okay, which is determined by long-term scheduling. And that's all I'm going to say about long-term scheduling. We are not going to go into any details of it. All you need to know is that it is there. The OS is keeping track of how many processes there are. And if you happen to hit those limits for any reason, you will not be allowed to fork new processes. Okay? Now, in contrast, short-term scheduling, as I said, is the problem of determining which process actually gets to execute next, okay, in the short term. Okay, so and that is where we are going to essentially focus all of our time. Okay, so every time this short-term scheduler runs, okay, it's going to look at the ready queue, pick one of the process, and let it execute. And there are many different goals that we can have for a short-term scheduler. We'll talk about that. There are some options, and there will be efficiency considerations as well. And we'll look at all of those. Okay. Any questions on long-term versus short-term scheduling? Yes.
Well, I have a question about long-term scheduling. Is it like all the states or just the ready state that applies to?
Yeah, okay. So the question is, does long-term scheduling apply to any state or just the ready? It actually applies to the new state. It only applies when you start a process. Okay, you're not actually scheduling it. When you start it, the long-term scheduler will say, okay, do you even allow it to start?
Okay.
Okay,
And
once
it
you're
takes into
in,
account.
you're in.
Okay.
Then there is nothing, then you don't get to be kicked out or anything. Okay.
Okay.
So it is just to decide how many processes even get to start up concurrently.
Okay.
Okay. Any other questions here? Okay. Right. So there are two types of short-term schedulers. Okay, we'll talk about what are called preemptive scheduling and non-preemptive scheduling. Okay, to understand this, let's first try to figure out when will the kernel run the scheduler. Okay, so essentially, if a process that is executing starts doing I/O, it is going to relinquish the CPU. The CPU is going to become idle, and then the scheduler has to decide which other process gets to run next. Okay. If an interrupt occurs when a process is executing, okay, you are going to suspend execution of the current process, okay, save its state, run the interrupt service routine, okay, basically go to the interrupt handler, handle the interrupt, and once the interrupt is done, the CPU is idle again. Okay, the scheduler now has to run and figure out which process gets to run next. Maybe you can just restart the process that was interrupted. Maybe you pick some other process. That's the job of the scheduler to decide. Okay? Or if whenever a new process is created or terminated, also the kernel is going to run, okay, in order to either create the process, okay, or terminate the process that has just finished, and then you have to decide what process is actually going to execute. Okay. Now in a non-preemptive system, okay, the scheduler must wait for one of those events to occur before it actually makes a decision. Okay. In other words, as the name non-preemptive suggests, you are not going to preempt a running process. Okay, once you schedule a process, you either let it run to completion, you either wait for it to do I/O, or you wait for an interrupt to occur. Okay? You are not going to interrupt the process otherwise and ask it to relinquish the CPU. Okay? In contrast, if you have a preemptive system, okay, you are going to use the notion of a time slot. When you schedule a process for execution, it will at most run through the end of its time slot. Okay? And then it has to give up the CPU. Or if during the time slot, if there is I/O or interrupts occur, you are also going to give up the CPU. Okay? In other words, in a preemptive system, you can preempt processes when their time slot expires and some other process gets to run. In a non-preemptive system, once you start running, okay, if you are not going to do any I/O, there are no interrupts, you can run for long periods of time. Okay? Other processes that are in the ready queue must continue to wait. Okay, they are not going to get a turn to run on the CPU until one of those three things happens for the currently running process. Okay, so most schedulers will be either preemptive or non-preemptive, and we'll look at examples of all of those.
Yes, so with a non-preemptive system, if the process runs more than the given time for it, is still going to be equal?
Okay. Question is, in a non-preemptive system, what happens if the process runs for more than its allocated time? So the thing to remember is, in a non-preemptive system, there is no such thing as an allocated time. Okay? You basically say run for as long as you want. That's the way to think about it. In a preemptive system, you are going to say run for at most your time slot. Okay? The non-preemptive system, once you run, you say basically run for as long as you need to until you finish, or until an I/O occurs in that process, or there's an interrupt. Okay? So there's no notion of switching between processes there. Is that clear? The two types of scheduling policies. We look at actual examples of both of these. Okay. So now before we go into the specific policies, we should ask, what are we trying to do with the policy? What kind of design goals do we have that will allow us to decide this policy is going to be better than this other policy? Okay. So here are some high-level design goals that you might have, okay, that you want to achieve in your operating system. Okay. Okay, you might want to maximize CPU utilization, which is utilization essentially is the percentage of time the CPU resource is busy. Okay? If you maximize utilization, you are making better use of your hardware, you are making better use of your CPU. Okay? You might want to maximize throughput. Okay? Throughput is defined as the number of processes that complete per unit time. How many processes, how many jobs are finishing per unit time. Okay? Higher throughput indicates that the system is able to run jobs faster. Okay? So you might want to pick a scheduler that maximizes throughput. Okay? You might want to minimize turnaround time. Turnaround time is the completion time of a process, the time from when it started and the time it finished. The shorter that time, the faster your process has finished. So that's also a good design goal to have. Okay? You might want to minimize waiting time. Okay, waiting time is the time you sit in your ready queue, waiting to get a turn on the CPU. Okay, while you are waiting, you are not making progress. That process is not making progress. Some other executing process is the one that's making progress. Okay, so you might want to minimize waiting time. Okay, or you might want to minimize response time. Response time is the time that elapses between the time you provide an input to the system and it shows you an output. Okay, maybe you type something on the command prompt, maybe you click a mouse button, and you want to see how quickly the system reacts to whatever input you are providing. Okay, that's called response time. In interactive system, the faster your response, the better your system is perceived. Okay, if you have slow response time, you feel like your system is slow, it's sluggish, it's not responding to your user input very quickly. Okay. So you might want to minimize response time in interactive systems. So as you can see, all of these are good design goals to have. Okay? And if you had a scheduler that optimized all of those things, that would be the best thing because you are trying to hit all of those goals. They all look like good things to have. Okay? But as we will see, okay, you will have to make trade-offs. Okay? Certain scheduling policies will optimize some of these things, but often that will come at the expense of making some other things worse. Okay? Because you can't actually optimize all of those things. If you try to make one better, it is probably going to come at the expense of something else, as we will see. Okay? So it is important for an OS kernel designer to figure out what kind of a system or what kind of applications are actually going to run on this system. And choose a scheduling policies that optimizes metrics that those type of applications care about. Okay? If it's an interactive system where users are directly interacting with the system, then maybe you want to optimize response time. Okay? And that might come at the expense of some of those other things. Okay? Because you are carefully tuning your system to make sure that when a user interacts or maybe touches a touch screen or clicks a mouse or types something on the command prompt, okay, that the system provides a response as quickly as possible. Okay, that's a good goal in interactive systems. Okay, or if you have batch jobs, then you might want to optimize turnaround time. Okay, the completion time of the job has to be optimized. Okay, that's a different design goal. So if you have a desktop operating system, maybe you will do one thing. If you have a server operating system that is a server that runs more jobs, you might pick a different policy. Okay? So there's no one policy that's going to be good for all of those things. You have to decide what kind of a machine is your OS running on, what kind of jobs is it going to run, and pick the right policy. Okay, so this is where you're going to have to start making trade-offs. Yes, question.
Is the scheduling algorithm, do you change that in an operating system, or is it pretty set in stone?
The question is the scheduling algorithm something you change or is it set in stone? So there are two ways to answer the question. Typically, an OS kernel might support more than one operating system scheduler or the scheduling algorithm in its code. Okay, but when you compile a kernel, you have to pick one. Okay? When you boot the kernel, you actually run that. That's why it's like if you go to the Linux source tree and look at the Linux scheduler, you'll see that there are 2 or 3 different schedulers in them. But when you compile a kernel, you end up picking one typically, depending on what you're customizing that Linux kernel for. Is it servers, is it some other kind of a machine and so on. Okay? Now there are a few operating systems, but they're relatively rare that will allow you to pick this at boot time. That they have multiple support compiled in and you can put. Okay, but they're rare. Typically it is determined for you and you cannot change it once the system is actually compiled. Any other questions? Okay. All right. So with that, so I already said all of this thing. You have to pick. All of these are good goals, but you can't actually hit them all. You have to decide which one is the best one. Okay. So now we are going to start looking at actual policies, and we'll make some simplifying assumptions so we can understand their behavior clearly. Okay. So we'll assume that you can have multiple users in the system, but each user has a single process. Okay. We'll also assume that processes are single-threaded. We don't have threaded processes where there are multiple threads. We'll look at scheduling processes with threads after we start talking about threads. For now, we don't know anything about threads, so we'll assume that all processes have a single thread in them. Okay? We'll assume that processes are independent, okay? Because if you have cooperating processes, there are specific policies that allow you to schedule them as a group. Okay? We are not going to look at those policies here. We are going to look at policies that assume processes are all independent from one another. Okay? We'll also assume that you have a single processor with a single core on your system. Okay? Uniprocessor system, single core. If you have multi-core, multi-processor system, then there are more general policies which we are not going to look at. Okay? Because even with these assumptions, we will see that there are some complex policies that you might have to come up with, okay, in order to make good design decisions. Okay? So those are our assumptions. Okay? And some of these assumptions have been with us since the 1970s, because that's when people, researchers started studying these policies. And even today, you will see that these policies continue to evolve. Okay? And if you even look at open source operating systems, and look at the scheduler, you see in the past 5-10 years, the scheduling policies still continue to evolve. They make them better in some regard or the other. Okay, so this is still an active area for many OS researchers. Okay, so we look at these 5 or so policies. Okay, so we'll start with first come first serve, and we'll do round robin, SJF, and we'll make them all little more complex policies in terms of MLFQ and shortest job first. Okay, so let's start with first come first serve. This is the simplest policy that you can imagine. As the name suggests, you are simply going to schedule jobs in their arrival order. Okay, which are, so you essentially you will have jobs in your ready queue. Okay, whenever the CPU scheduler runs, you are going to pick the job at the head of the queue. Okay, that's the first job because they are queued up in FCFS order. You will let that job execute, and this is a non-preemptive system. You will let it run through completion. So you will not have time slices in first come first serve. When a job is scheduled, you will let it run for as long as it needs to. It can run to completion, or if the job starts printing something onto a file or some such thing, it starts doing I/O, it will have to give up the CPU, and then you will run the next job in the ready queue. Okay. So essentially, jobs are scheduled in arrival order. They are scheduled to completion. Okay, so do not relinquish the CPU unless you do I/O. Okay, and essentially, it's a non-preemptive system as a result. Okay, is this clear? Very simple policy. So let's talk a little bit about pros and cons. Okay, well, first let's do an example, then you can talk about pros and cons. So here are 3 scenarios shown in this picture. Okay, you have jobs that arrive in order B, C, and A. Okay. There's no I/O in that scenario. So you'll run job B. Okay. Its length is 2 units, so it runs all the way through completion. Then you run C, and then you run A. Okay, because that's the order in which they arrived into the system. That's the order in which the user started them up. Okay. If the arrival order was A, B, and C, okay, then you would have run them in order A, B, and C. They're the same job. They just happen to start up in a different order. You run them in a different order. Okay. And if it so happens that in that order, A actually is a job that does I/O somewhere in the middle, you do run A first, but you only run it until it does I/O, not through completion. And then when it does I/O, it goes to the wait queue. Okay, it's no longer executing on the CPU. Yeah, at that point, you look at your ready queue, which still has B and C. So you'll run the next job, which is B. B runs through completion. Okay, and then maybe A finishes its I/O, comes back into the ready queue. Okay, and then it gets to run again because it came first in the system, and then you run C. Yes, question.
Why is it that it's the same amount of time, whether or not it's like in the front storm back or takes IO and CPU time?
Okay.
It always takes 5 units.
So it is assumed that job A requires 5 units of computation. Okay, let's say there are 5 instructions in job A. Okay, let's say each of those instructions takes 1 unit of time. So to execute the job, doesn't matter what order you run, you're going to execute those 5 instructions in order to complete the job. So it will always take 5 time units. In the order in which you run the job, it's not going to matter at all. The time to execute all the instructions in a program that determines how long it needs to run on the CPU, not the order in which it runs. Okay? Yes.
There would be some time overhead from the context switches.
Yes. So question is, will there be time overhead in context switches? There will be time overhead in context switches, but here there are no context switches other than when you do I/O. when we talk about preemptive schedulers, we'll see that context switches are frequent, and then optimizing context switch overhead is important, but not so in FCFS. Some other hand up somewhere. Okay, so this is FCFS. Okay, it's essentially a very simple scheduling policy. Doesn't do a whole lot of sophisticated things. Okay, so the advantage is it's simple. The disadvantage is that the waiting times of jobs can be very long. Okay, and here is this example should tell you why that is the case. Okay, so waiting time is the time you are going to sit in the ready queue waiting to run. Okay, so waiting times can increase if you have some short jobs and some long jobs. Okay, in particular, if the long job arrives before a bunch of short jobs and it gets to execute, these short jobs are going to have to wait for a long period of time for this long job to finish. Okay. That's what is shown here. Okay, so here A is the long job and B and C are shorter jobs. Okay. If A gets to run first, B and C have to wait 5 and 7 time units. Okay. In the other case, if the short jobs actually run first, you'll see that they run quickly, they finish, and then the long job gets to run. Okay. The total time for all of those jobs is identical in both of those cases, but the amount of time a job sits in the system waiting is different in those two cases. Okay. This is the same, intuitively, this is the same issue that might occur if you are actually driving on a freeway and you get stuck behind a big truck. Okay. And there's a long line of cars that are just following the truck because the truck is slowing everything down. Okay. Because it's a larger vehicle, it's slowing down smaller vehicle. It's the same kind of problem. The long job runs, yeah, and then all of these other jobs have to wait, and then they run relatively quickly. Okay, that's a disadvantage of the system, is that the waiting times actually can vary dramatically. It depends on the order of arrival, and in particular, it also depends on whether some long jobs get in first, and then they make a whole slew of short jobs wait because they are executed. Is that clear? Any questions on this? Okay, so that's the disadvantage of FCFS, variable waiting time. Okay, let's look at the next policy now. Okay, this one is called round robin. Okay, it's also a very straightforward policy. So in fact, it's the simplest preemptive scheduling policy. Okay, in round robin, okay, every job when it gets to run, okay, I'm going to use the term job to mean a process. Okay, they mean the same thing. Okay. When every job gets to run, it is going to be given a time slice. Okay. It can use up its entire time slice, at which point it has to relinquish the CPU. Okay. Or if in the middle of its time slice it executes an IO instruction, it automatically gives up the CPU because IO means you have to go into the wait queue, you invoke a system call and you have to wait for IO to finish. Okay. So essentially, you are going to schedule jobs in your ready queue in round robin order. Each of them is going to be given a time slice. Once this time slice expires, that if it's still runnable, it goes to the end of the queue, and essentially you are going to cycle between these jobs, which is why it's called round robin. Okay, so a few things to keep in mind. There is a notion of a time slice. Okay? Unlike FCFS, you can't run for long periods of time as long as you want. You can run, once you get to run, you can run for at most your time slice, okay, no more. That's the first thing. Okay, so it is preemptive, you can run for at most your time slice, and everyone gets a turn. Okay, all the ready jobs are going to cycle, and you get a turn to run on the CPU. Okay, yes, question.
Is the time slice the same for every process, or can it vary?
Okay, is the time slice the same for every process? So the time slice is going to be a system parameter. It's a parameter that the scheduling policy is going to pick, and it's going to be the same. Okay? In this policy, because shortly we'll see other policies where the time slices will differ, but in this policy it's the same. Okay, yes.
That's a good question. So if it runs out of time, we move it to the back of the queue.
Yes.
And when it gets to its turn again, does it still use the same time slice as before?
Yes. So let's assume your time slice is 1 millisecond. Okay. So if there are 5 jobs, you are going to give each of them 1 millisecond. Once you finish them, if none of them, let's say, do any IO, then you again do repeat. Okay, so you do job 1, job 2, job 3, 4, 5. Go back and say 1, 2, 3, 4, 5. Each of them gets 1 millisecond every time they run. Okay? Yes.
Well, when a call is made to IO, does it move to the back of the queue?
What is the question? If it does I/O, what happens?
Yeah.
Okay, if you do I/O, you are going to not go back to the ready queue. You are going to go to the wait queue. I'm going to back up a couple of slides here. Okay, so let's look at this. Okay. So these are our ready jobs. Okay, you are doing round robin across these jobs. Okay. If this job is running here and it starts doing an I/O in the middle of its time slice, it is actually going to go to this queue. It's going to go and wait. So these jobs are not actually running. They're simply waiting for their I/O. They're sleeping, waiting for their I/O to finish. Okay. Once their I/O completes, they're going to rejoin the ready queue. Okay. And then you are just simply doing round robin here. You don't care about what's happening in the wait queue. Okay. So your round robin is simply looking at all the ready jobs and you're simply doing round robin. That's all you're doing. Okay. Any other questions? Yes.
So just to clarify for that situation, it waits for the IO and then it gets to the back of the queue and then waits for it.
Yes. So if you are done with I/O, okay, you rejoin the queue. Where you rejoin the queue is up to the scheduler. Let's say for simplicity, you just rejoin the end of the queue. You could even rejoin the front of the queue. That's up to the scheduling policy. Okay? But we can just assume that any job that arrives, whether it's a new job or a job that's finished I/O, just has to go to the back of the queue because that seems like a better policy. Okay, if you're just arriving at any queue, you typically join the end of the queue, not the beginning. Okay, so that's basically what round robin would do. So it's important to keep in mind you're simply doing round robin between these processes here. Okay? You don't care about what's happening here, neither do you care about what new processes that are being set up. Once they are ready, they will join the ready queue. Okay? You're simply cycling between the ready jobs. Okay? So now let's come to the question that was asked earlier, which is the context switch overhead. Okay? In round robin, every time a time slice expires, you are going to do a context switch. Yeah, because you're basically the job is run through its time slice, it's time for some other job to run. Okay? So you're going to save the state of that job in the process control block, pick the next job at the head of the ready queue, restore its state and get it to run. Okay, all of that is bookkeeping overhead that you're going to incur. Okay, that's extra overhead that the scheduler has to incur in order to run the next job. Okay? So all context switches have some overhead associated with them. Okay? And now depending on the length of your time slice, the overall overhead will vary. Okay? So for example, if you make the time slice very small, let's say you make the time slice 1 millisecond. Okay? And let's say context switches take 0.1 millisecond. It takes a tenth of a millisecond to save the state and restore state of the new process. Okay? So now you just put a 10% overhead in your system. For every 1 millisecond of useful execution that's occurring, you are wasting 1/10 of a millisecond doing bookkeeping and just switching between processes. Okay? So that's a 10% tax that the OS is paying for simply running processes. Okay? On the other hand, if you had made the time slice 100 millisecond, okay, and your context switch time is still 0.1 millisecond, okay, so then every process is going to be given 100 millisecond. Once it finishes, then you are going to spend a tenth of a millisecond switching between processes. The next process gets to run another 100 milliseconds. Okay? So for every 100 millisecond of useful execution time, a tenth of a millisecond is actually getting wasted doing context switches. Okay? So now your tax on the overhead has gone to 0.1% from 10%. Okay, this is going to be a more efficient system because you are making better use of your CPU cycle. Rather than wasting a tenth of your CPU cycles just doing bookkeeping, you're only spending a tenth of a millisecond, 0.1% of your cycles doing bookkeeping. So a choice of your time slice has important implications on system efficiency. Okay? And there are trade-offs. It's not like you can make it very large. There are some downsides to that as well. If you make your time slice too large, your waiting time is going to suffer. Okay? As you make your time slice larger and larger, the behavior of round robin starts looking more and more like FCFS. Okay? In the limit, if you set your time slice to infinity, okay, round robin becomes the same as FCFS. FCFS is round robin with an infinite time slice because you never ask this process to give up the CPU. You let it run through completion. That's like saying you have a time slice of infinite duration, run for as long as you want, and once you finish, I'll run the next process. Okay? So you can imagine as you make it larger and larger, you are essentially going to look more and more like FCFS, which means waiting times of other processes is going to suffer. Okay? It will also impact interactive response time. As waiting time increases, it also impact response time. Let's say you do a mouse click. Okay? If your time slice is 1 second and there are 5 processes queued up ahead of you in the ready queue, okay? It will take 5 seconds for this process to even run and start processing your mouse click. So your user in the meanwhile is waiting there, waiting for the system to respond, and the system is simply running other processes that are ahead of it in the ready queue. Okay? And this will make your system look extremely sluggish because it has high wait times. Okay? So if you basically make your time slice too large, waiting time will suffer it, response time will suffer, it will start looking like FCFS. On the other hand, if you make it too small, it's going to be a highly responsive system. Everyone is, you're cycling between processes very quickly. Okay? Every process is getting a turn on the CPU rapidly. Okay, you run for short periods of time, but you rapidly cycle between processes. So you all make a little progress. Okay? So in this case, your response times will be good, but as I said, your efficiency will go down because you are still paying that context switch tax. Okay, the shorter your time slice, more context switches that are going to occur every minute. Okay? More context switches is more overhead. Okay? So you have to balance between these trade-offs. You don't want to set your context switch time to be too large, okay, which will make it behave poorly from a user perspective, or make it too small, which will make it behave poorly from an efficiency perspective. So you need to find some middle ground. Yes, question.
Can this length of the time slice be dynamic at all, or is it set in stone upon kernel?
Okay. Question is the time slice set in stone? Can it be dynamic? In this policy, it's set in stone. You pick based on whatever your expected behavior is. But we'll see other policies where you can modify it and try to do things like that. But here, this is a simple policy. You pick a time slice, okay, and you're done with it. Okay, so and a good trade-off is to say, I don't want to pay more than 1% tax. Okay? The context switch time should not be take more than 1% of what a time slice is. Okay, so essentially you can see what your context switch time is. So let's say it's 0.1 millisecond. In that case, you can have your time slice to be 10 milliseconds. Okay, or if it's the context switches take 1 millisecond for whatever reason, then you should set your time slice to 100 milliseconds. So for every 100 milliseconds of useful work, you're spending 1 millisecond on overheads. Okay, that's a 1% tax. Okay, that is going to give you a reasonable balance between efficiency and responsiveness. Okay? Or that's a design rule that is typically followed. Saying let's limit it to 1%. That's the way you can choose it in a reasonable way. You could have said let's limit it to 0.5%. Whatever your favorite metric is as a kernel designer, you can pick, and that will give you some reasonable guidelines on how to pick it. But once you have chosen your time slice, in round robin it's fixed. You cannot change it. Okay, so it's basically going to stay the same for that curve. Any questions here? Yes?
So the context switch time is always constant, right?
The context switch time is constant, more or less, yes. Because you are simply doing bookkeeping, you are taking all the registers, saving them in the process control block. You will run your CPU scheduler, which is going to simply, in this case, look at the head of the queue and pick the next job. For that job, you look at the PCB and take all of his registers and restore them. And then that process is done. Okay, so all of those operations are going to take a fixed amount of time. Okay, so that's your round robin policy. So there are some advantages and disadvantages. It is a fair policy because you're cycling between processes. You're not favoring any one process. Everyone gets a turn to run on the CPU so long as you're in the ready queue. You get the same time slice. Okay, there is no favoring one kind of job or the other. Okay, so it has good fairness properties. Okay. Disadvantage is the average waiting times can actually be bad, as we will see in just a moment. Okay. Even though you are fair, so in this case you are getting fairness at the expense of waiting times. Okay. The jobs might wait for longer times than other policies. Okay, so let's do an example, a numerical example, just to go through this in a little more detail. Okay. We'll assume that you have a system with 5 jobs. 1 through 5. Okay. Let's also assume in this case that all jobs require 100 units of CPU time, okay, in order for them to complete. Okay. And for simplicity, we'll assume that jobs don't do any I/O in this case; they only compute. There's no I/O, and the time slice is 1 second. Okay. And we'll also assume context switches don't cost anything. Okay. They are zero overhead, because we are simply trying to understand how FCFS and round robin compare with one another. Okay, so we'll assume that all jobs arrive at time 0, but in that order. Okay, 1, 2, 3, 4, 5. They all arrive, they're queued up in that order. So we'll take FCFS. Okay, so what's FCFS going to do? Which job will run first? Okay, the first job will run. It's doing FCFS after all. So we'll run the first job. Okay. In FCFS, the time slice does not matter. Okay. It's a non-preemptive policy. You will run the job saying job 1 you get to run, and it will take its entire 100 seconds to run. Okay. All other jobs are still waiting. It will run first 100 seconds. Nothing else is happening in the system. Only job 1 is running in FCFS. Okay. And job 1 finishes at time t equals 100 seconds. Okay. FCFS will pick the second job. It will execute. It will run for another 100 seconds. Okay, and then it will finish at time 200 seconds, and 3 will run, same thing will happen, then 4 and then 5. Okay, at time t equals to 500 seconds, all jobs are finished in FCFS. Okay, they are run in the order 1, 2, 3, 4, 5. That is the order in which they arrive. Okay, so that's the behavior of FCFS. Okay, that's what we expect. Now let's analyze round robin. Okay, in round robin, what will happen? Which job will run first? Okay, the first job will run. Okay, you are doing round robin in the ready queue. Okay, how long will it run for? It will run for its time slice, which is 1 second. Okay, you are given a time slice of 1 second, which is what is mentioned there. Okay, time slice. So you get to run for 1 second. At the end of that second, it gives up the CPU because its time slice expired. Okay, it goes back to the end of the ready queue. Okay, job 2 will run next. It will run for another 1 second. Okay. And then it will go to the end of its queue. And then 3 will run, and then 4 and 5. Okay. At the end of the first 5 seconds, each job has gotten 1 second of time on the CPU. Okay. Already they have started executing and made some progress. Compare that to FCFS. In the first 100 seconds, nothing happened other than running job 1. All other jobs are waiting. They did not get any CPU time at all. Okay. Here we are cycling between jobs. Okay. And this process will continue. Okay. At the end of 5 seconds, each of them has gotten 1 second of CPU time. Okay. The time they still need to compute is now going to be 99 seconds. Okay. Because each of them needed 100 seconds of time, they all used up 1 second of compute time. Okay. So you will repeat. Okay. You will again do 1, 2, 3, 4, 5, and so on and so forth. Okay. So now when is the first job going to finish? If you continue with this policy. 500 seconds. Okay. When will the second job finish? Okay. All right. So the first job will finish when it gets the 100th time slice. So each job is getting 1 second of time slice, and it needs 100 time slices to finish because it has 100 seconds. Okay. The first job is going to get its 100th time slice at time 495. Okay. It will finish at 496 seconds. Okay. That's when it will finish. And then the second job will finish at time 497, 498, 499, and 500. Okay. So again, all jobs will finish at 500, but you'll see that the behavior is very different. Okay. All jobs are in the system for a much longer time in round robin than in FCFS. In FCFS, the first job is already departed at time t equals 100 seconds. There are only 4 jobs left in the system at that point. Okay, and then the second job departs, and third job departs at this point, and the fourth and the fifth. Okay. So in this case, the jobs have very different lifetimes. The first job is actually left the system long before the last job finishes. Okay. In this case, they are all finishing more or less at the same time, okay, within 5 seconds of one another. Okay. So all that is saying is same jobs, same amount of computation, 2 different policies cause them to behave very differently in terms of when they finish, how long they are in the system, and so on. Okay. So this should tell you that the scheduling policy has a big impact on how the jobs actually behave in the system. Okay. Now let's look at this column, which I already put the numbers, but I'm going to back up a little bit. Okay, so this column asks you to compute the wait time. Okay. So the wait time is simply the completion time of the job, okay, minus the job length. Okay. So that's the amount of time you spend waiting. Okay. Wait time is how much time did you spend waiting on the ready queue. Okay. The time you spent waiting on the ready queue is the time you finished minus your compute time. Okay. You spend 100 seconds of time on the CPU computing. Okay. Let's say you finished at time 500 seconds. It follows that the remaining 400 seconds were spent waiting in the ready queue. Okay, so if you want to compute wait times, you're simply going to take this column and take the difference of the two. Completion time minus the job length typically gives you the wait time. Okay? If you have different arrival orders, you have to also subtract the arrival time. Okay? In this case, you all arrive at the same time. Okay, so the difference between these two columns, okay, is going to give you the wait time for FCFS. The difference between these two columns is going to give you the wait time for round robin, okay, which is what you will see. Okay? You will see that the wait time for the first job in FCFS was 0. Okay? It arrived in the system, it immediately got to run, and it finished. It never spent any time waiting at all. Okay? The second job waited for 100 seconds, okay, because it finished at 200 seconds. Of those 200 seconds, it computed for 100 seconds, and it waited for the first 100, waiting to start executing. So its wait time is 100, and so on. So you see that the difference between these two columns is actually giving you this. Okay. Now in the case of round robin, it's the same thing, the difference between these two columns. Okay, this job, the first job finished at 496 seconds. Okay, and over its lifetime, it spent 100 seconds on executing on the CPU. Okay, so it follows that it spent its remaining 396 seconds just waiting in the ready queue. Okay, because you're not computing, you're sitting in the ready queue waiting for a turn. Okay, there's only two things you can do. Okay, so you will see that here the wait times are 396, 397, and so on to 400. Okay. Now, if you take the average waiting time in the system, you will see that you will get very different results. Okay, if you take the average of this column, the average of this, you will see that the average wait time for the jobs was 200. In this case, the average was 398. Okay. So you can argue based on this example that round robin was more fair. It gave every job a turn on the CPU. Okay. But it increased the wait times for all the jobs. So you got fairness at the expense of worse average waiting time. Okay. FCFS was not a fair policy at all. It simply scheduled jobs in the order of arrival, and if you just happen to arrive last, too bad, you wait for longer. Okay. But the average wait time is still less than in round robin. Okay. So you are trading fairness against wait times in this case. Okay, so this is why I said you cannot just have fairness and good execution times and good wait times and good response time. Often one will come at the expense of the other. Okay, this is a very simple example to show you that that's actually what's happening. Okay? Questions on this? Alright, so I think I have another example which I'm going to go through far more quickly. Okay, so here are jobs that still all arrive at time 0, but they are unequal in length. Okay, they're not all identical jobs like the previous example. Okay, so in this case, the job length is 50, 40, 30, 20, and 10. Okay. Again, you can, as is mentioned there, the time slice is set to 1 second. There is no I/O. They are all CPU-bound jobs, and context switches don't cross. Okay. As you can imagine, you should expect questions of this sort either on the homework or an exam where you are given a scenario like this with maybe different arrival times or some I/Os or jobs and so on, and expected to work this out. Okay. So in this case, if you do FCFS, they'll run in the order 1, 2, 3, 4, 5. Okay. Job 1 will finish at time 50. That's its length. Job 2 will finish at time 90. Okay, because it starts at 50 and it computes for another 40 seconds. Okay, so it finishes at time 90. This one finishes at 120. This is going to be 140 and this is 150. Okay, so at time 150 they will all finish. Okay. Round robin will cycle through them 1 second at a time. Okay. So once all jobs have received the 10th time slice, you will see that job 5 has actually gotten all of its computation time. It needs 10 seconds. Each time slice gives it 1 second of compute time. So it needs 10 time slots overall before it finishes. So in the 10th round of your round robin, job 5 will finish. Okay, it will be done. Then you are going to cycle between jobs 1, 2, 3 and 4. Okay, because 5 is done. So you are cycling between 4 jobs now, not 5. Okay, you will go another 10 rounds. Okay, at which you have finished 20 rounds. Okay, then this job is going to finish. Okay, then you have 3 jobs left. You are going to round robin between those 3 jobs. Okay, we'll wait another 10 rounds elapsed. That's 30 rounds at this point, and this job will finish because it has run 30 times. Okay, these 2 jobs are still computing. Okay, then you basically run those 2 jobs in round robin order. Okay, in the 40th round, okay, basically this job will finish, and then you will just execute that job. Okay, there's nothing else to round robin between, and then you will finish. All jobs will finish. Okay, so you will see that the completion times here are the opposite. Okay, this job is going to finish in the 5th round. Sorry, in the 10th round. Okay, that's going to be 50 seconds. Okay, because there are 5 jobs, you're cycling between them. Each round takes 5 seconds. Okay, basically you finish 10 rounds at time t equals to 50. Okay, so this job is done at 50. Okay, then you're doing round robin between these 4. You can compute it. You will see that this job finishes at 90, 120, 140, and 150. Okay, so in this case, the average completion time is the same. Okay. The wait time is always the difference between these 2. And the wait time for this job in this case is 150 minus 10, so 140. Okay, here is 140 minus 20, 120, and so on. And for round robin, it's the same thing. You take the completion time, you take the job length, take the difference. That's the amount of time you wait. Okay. So it just so happens that in this case, round robin is able to match FCFS, okay, in terms of wait times. Okay. That's simply an artifact of this example we have concocted. Doesn't mean that in general FCFS is going to match performance of the round robin will match FCFS. Often it will do poorly, as we saw in example 1. In terms of wait time, in terms of fairness, it does the best job it could. Okay, but in terms of wait time, it will often do worse. But this example shows you sometimes that's not the case. They behave in the same way. That just depends on the length of the job, when they arrive, what's happening, and so on. Okay.
So if there's a lot of like variability in the length, would it generally have a better would the round robin have a better wait time?
Okay, so the question is that wait time better because of variability? In this case, it was not so much as the variability, just an artifact of how we pick the job.
Large range and length.
So typically what happens is, if you have variability, you are going to essentially get better average waiting times, but the overall thing might get worse because you are fair. Right? So you are just cycling within the job. You don't care when they arrive. You don't care how long they are. You are just saying these are all the jobs. Everyone gets a turn. It doesn't matter how much time you need or when you arrive. So it's basically looking at jobs from a very different perspective. FCFS actually takes when did you arrive. You see other job policies that say how long is this job.
Right. Okay. Yes.
There's only one process on round robin ready queue. Does it still time slice it and do context switches?
That's a good question. The question is if the ready queue has only one job active, okay, will it still time slice or not? Okay? So you will keep time slicing regardless. Okay, but since you are the only job, you will be evicted from the CPU. Go to the back of the ready queue, you are still the only jobs you get to run next. Okay? So you might be wasting context switches, but there is no way for the OS to know that no other jobs are going to arrive while this job is running. So you will still time slice. Okay, even though that might cause extra context switches that you could have avoided. But you will continuously run between across time slices. But there will be brief interruptions due to the context switch. Any other questions? So let's move on to the next policy. Okay, this is the third of our policy. Here we have two variants. Okay, let me explain each one. So this policy is called shortest job first. SJF is the acronym. Okay, so we'll talk about that. Then we'll look at the other acronym there, which is called SRTF, which is shortest remaining time first. The reason there are two variants is that this policy has a preemptive variant and a non-preemptive variant. So this policy comes in two flavors. You can either pick the non-preemptive version or the preemptive version. Okay? In case of the previous two policies, they are one or the other. This policy can be either one depending on what you want to do. Okay? Let's first pick the non-preemptive version, which is shortest job first. Okay? As the name suggests, what this policy is going to do is it is going to look at your ready queue and pick the shortest job in the ready queue and run it to completion or until it does I. It's a non-preemptive policy. So always you pick the shortest job and let it run. Okay? In the non-preemptive version, you let it run to completion. In the preemptive version, you are time slicing. Okay? So you pick the shortest job, you run it for a time slice. Okay? And then it becomes even shorter job because you just finish some computation. If there are no other shorter jobs, it will again run because you're just context switching. You'll still pick this job. At each point, you'll look at the ready queue, pick the shortest job and run it. Okay? So in this case, you are actually looking at job lengths to figure out if which job to run. FCFS looked at the arrival order. Okay? Round robin said it doesn't care. It runs all the jobs one after another. It doesn't look at the length. It doesn't look at their arrival order. It simply schedules them all one after another. Shortest job first is going to say look at the length of the job. If the shorter the job, it gets to run with higher priority. The shortest one always runs first. So you are favoring short jobs over long jobs, as you can imagine in this case. Okay, is that clear? So there are some advantages here. You can prove, which I am not going to prove, but I am going to assert that you can prove that shortest job first has optimal wait times. Okay, that waiting time column that I have been looking at, if you look at shortest job first, you can show that no other policy can outperform what shortest job first. If that is what you want to optimize, shortest job first is the one you go with. There's no other policy that can do better, okay, because it gives optimal average waiting times. Okay. The other advantage is it has a preemptive and a non-preemptive version. Okay. So essentially you can pick depending on what kind of system you are in. Okay. And as a result of favoring short jobs, you will see that implicitly you are going to favor IO bound job over CPU bound job. That may not be apparent yet, okay, but as you see the next policy, you will see why favoring short jobs implicitly favors IO bound jobs over CPU bound jobs. Okay, but at this point, I'm just going to say this, but when you look at MLFQ, you will see why that is the case. Okay, but now, what are some disadvantages of shortest job first? It's the policy with the optimum waiting times. Okay? But it is not a policy you can actually implement in any real operating systems. It's not practical. Why is that? Any thoughts? Why would SJF be an impractical policy? Yes.
We have a job that takes a lot of time to be almost
Okay, so you're talking about properties, you're talking about the next disadvantage, which is long jobs can starve. It's absolutely true. That's not why it's impractical. Yeah, I'm asserting that it is not possible to implement this in a general purpose operating system. Yes. Okay, so that's the right observation. Shortest job first require knowledge of the job length. Okay. How is the OS to know how long a job is going to run? So let's say you start up your browser. Okay. Does the OS know how long you are going to run this browser? You may yourself not know how long you are going to keep it active. How is the OS going to know this? At any job you start, you need to know the job length in order to pick the shortest job. Okay? So knowledge of job length is essential for implementing this policy. But the OS is not going to know the job length. It may not know how long a job runs. Sometimes the length of the job may be determined by the input, what's happening, because there may be branches in the job. The job executions are not predictable. Okay, you can make guesses of how long it might run, but it's only a guess, it's not a guarantee. Okay? So in any operating system, it's not practical to assume that when you start up a process, you will know the length of the process, okay, the compute requirements of the process. If you don't know that, you cannot implement shortest job first. So there is no way for you to figure out which job is longer and which one is shorter. Okay? So it has a property that's a good one, which is it optimizes wait time. But it is impractical to implement in any real system because it needs knowledge of job length. If somehow this knowledge was available, this would be a good policy. Yeah, but in most operating systems that are general purpose in nature, that's not a practical assumption. You can't expect the user to specify every time you start a process, say, I'm going to run it for 5 minutes. And users don't want to do this. You just want to run your application, not tell the OS unnecessary information. Yeah, so it's not a practical policy to implement. Okay. Having said that, let's still look at an example to see how it behaves. Okay, so this is the same example as the previous one, okay, but with shortest job first column added to it. Okay, so I'm not going to look at these two columns. We already did this same example. Okay. Remember that shortest job first is a non-preemptive policy. SRTF is a preemptive version of it. Okay, so let's ask, if you had these jobs and you're doing SJF, which one would you pick as a scheduler? Okay, you'll pick job 5 because it is the shortest job. In this case, the job lengths are given to us. Okay? In general, you will not know this, but here we have specified it in the example. So you just look at the length of the job. Okay, which one is the shortest job? It is this job. It only needs 10 time units. So you are going to run it first. Okay? It is going to run to completion because this is a non-preemptive policy. Okay? So it will run for the first 10 seconds, okay, and then it will exit the system. Okay? And you have 4 jobs left. Okay, you take the next shortest job, or you take the current shortest job, okay, which is in this case job 4. So you are going to run that next. Okay? That will run to completion. Then you run this job, and then job 2, and then job 1. Okay? So FCFS looks at arrival order. Okay? Since they arrived in the order 1, 2, 3, 4, 5, it actually schedules them top to bottom. Okay? SJF looks at the job length. It just so happens that these jobs are sorted in descending order of job lengths. Okay, so in this case, you are going to start from the bottom and that's the shortest job, that's the next shortest job, and so on. So you are going to schedule in SJF, starting with job 5, and then job 1 gets to go last. Okay? Round robin is just cycling between them. It doesn't care about the arrival order or the length. Okay? It's just scheduling all of them 1 second at a time. Okay? So in this case, job 5 finishes at time 10 seconds. This one will finish at time 30 seconds, then 60, 100, and 150. So you will see that the average completion time has dropped. Okay, that's the average of those values. And then if you take the difference between these two columns, it gives you the wait time. Okay? Job 5 has 0 wait time. It's going first in SJF. It doesn't wait. Okay? So it's 0. Job 2 starts at time t equal to 10 seconds as soon as this finishes. So it waited 10 seconds. Okay? Job 3 starts at 30 seconds. It waited 30 seconds in the system and so on. If you take a mean of those, you'll get 40. Okay? So now you see that the wait time is actually half of the other two policies. Okay? And this is basically what I said, that SJF gives you optimal wait time. So it's going to outperform most policies on this metric. Okay? So you will basically get, and there is no way better. Okay? 40 is the best you can do. No other policy can do better. That's a proof which I have not proved here, but you can just take it as an assertion for this at this point. Okay? So it's optimal in terms of wait time. Any questions? Yes?
What was the origin of the process?
The processes all arrive at time 0, but we just assume that they are queued up in the order 1, 2, 3, 4, 5. Okay, they all arrive at the same time, but you put them in the queue in the order 1, 2, 3, 4, 5. So FCFS will schedule them in the order 1, 2, 3, 4, 5.
At that time, when shortest SGF started working, it looked at everything.
Yes, so all of them have all arrived at time 0. They are all in the queue at the same time. If they arrive in different orders, of course, different things may happen. In this case, they all arrived at the same time. Okay? Any questions on this? Okay. So if you had done SRTF, what might have happened? Which one would have been scheduled first? SRTF is SJF with 1 second time slice. You pick the shortest job, but you run it for 1 second time slice rather than running it to completion. Yes.
Which would do the same thing.
Okay, it may do the same thing, but let's work through that to convince ourselves it will do this. So which job will you pick first? You will pick 5, the shortest job. Okay? You run it for one time slice, 1 second. Okay? At which point it will go back to the ready queue. Okay? Now you have to pick again. Which job are you going to pick now? You will pick the same one. Okay, because you are going to look at how much time does the job have to finish. Okay? At this point it has 9 seconds of CPU time left. This is why you will pick it. Okay? This one now needs 9 seconds after the first context. So these still need 20, 30, 40, 50. Okay? So what SRTF will do is it will actually look at how much more time do you have left before you finish, which is why it's called shortest remaining time first. It will look at the remaining time of the job. At the beginning, the remaining time of the job is the job length. But as you compute, the remaining time keeps decreasing. Okay, so you'll still pick the same job because it just becomes even shorter. It needed 10 seconds, now it needs 9. It's an even shorter job. So you'll pick it again. It'll run for another 1 second. Okay? And then it will essentially need 8 seconds. You'll pick it again and so on. Okay, so you will actually do the same thing, but you will context switch. If some of these jobs were to do I/O, or some other jobs were to arrive in the system, you will see a different behavior from SJF. In this case, no new jobs are arriving and there is no I/O. So it will behave the same way. Okay? Alright, so just to make this a little more concrete, I am going to do a little example which requires some volunteers, specifically 3 volunteers. Anyone wants to volunteer? No. Okay. You volunteer, need one more volunteer. Okay, you need to come up. Okay, so we are going to demonstrate live how shortest job will work. Okay? So, you are going to be running a job. That's your job. Don't do anything with the paper. I'll explain how this is going to work. That's yours. And that's your job. Okay? So, we will assume that you need to run those jobs. And after each time slice, you are going to give me that piece of paper at the front. Okay, and that's how much time you have left. Okay, your job is going to require 4. Okay, your job is going to require 3, and your job is going to require 2. And you are all in the ready queue. Okay, that's the CPU. Okay, so you have to show that to them. Okay, that's so. So which job they think will run first? This is SRTF. Okay. So that's 2, 3, and 4. So you are the shortest job. See, so you get to run. So you get to sit here. Okay. So now you will run for a second. Okay. Give me the top piece of paper. Okay. So this job ran for a second, but now this job decided to do I/O at the end of its time slice. Okay. So you have to now leave the CPU and go to the wait queue. You can look disappointed. That's the ready queue. Stand in some other queue. So you are the next job. No, you are in the ready queue. You have to go to the wait queue. Okay, so that's a different queue. Yes, thank you. All right. So now you are going to run for a second. So you are going to give me the top piece of paper. So now you have 2 seconds left. You have to go back to the ready queue. Okay. How long is your I/O?
1 second.
Okay, so I/O is 1 second. So 1 second has elapsed while we ran this other job. Okay, we ran your job, so you rejoin the ready queue. And you can give me that piece of paper. Right. So now you have 1 second still to go. Okay, and you have what, 4? And you have 2 seconds. Okay, so who's going to run next? Okay, so you are going to run next. Yes, you get to sit here. All right, so you get to run for a second, you can hand me that paper. So now you are done, so you get to go to the finish queue, which is here. Okay, don't yet go. So now we are left with 2 jobs. Okay, so you are going to run. You have to wait, unfortunately, for a long time. You are a long job. Okay, so you are going to come, then you have to go back, and then come back again. You can look annoyed, it's okay.
No.
That's what shortest remaining time does. Okay, thank you. Now you are done. Now you can go back. Okay, so now you have to sit and get up 4 times. Okay. So now you can go back to the end queue, and you can all applaud for showing you how short is remaining time. All right. So you saw some nuances here. Okay, one nuance was what happens when you do I/O. So you go to the wait queue and you have to rejoin. That's your question.
So this job, when you did the 1 second and then had the 1 second of I/O,
Yeah.
why did he still go to the wait queue? Because he already used 1 second of CPU time. So should he go back to the ready queue and then when he goes to the running, then that triggers the I/O and then go to the waiting? Like I don't know why.
Okay, so that's a good question. The question was the first time slot, the shortest job ran for 1 second, and then it did 1 second of I/O. So why was it that the job had to go to the wait queue and wait a second? Did that time on the CPU not count? That's your question, correct? So what you get on the CPU is compute time. That's when you are executing. Okay, that 1 second of I/O was actually the time to actually do I/O. So let's say you are reading from a file. You ran for a second, you ran some instructions, and then you just opened a file and started reading some data from it. Okay? That 1 second of I/O meant that it took you 1 second to actually read some data from your disk. Okay? For that period of time, you are going to wait. The time that you are computing on the CPU doesn't count towards that time because you are actually executing instructions, not doing I/O. So they are 2 different things. It just so happened that your time slice and the I/O time were both 1 second. Just an artifact of the example, but they are 2 completely different things. Okay? Yes.
So would if I only took half a second, would it interrupt that time slice, or would you wait until the time slice is finished and then process it?
So that's a good question. The question is, the I/O took only half a second. What would happen? Would you interrupt it? So typically, what would happen in a real OS is, as soon as the I/O finishes, you will raise a hardware interrupt. Okay? To raise that hardware interrupt, you have to interrupt whatever was running on the CPU. Okay? Even though it's in the middle of a time slice, you essentially suspend that job. The OS runs. The OS will look at the I/O, okay, and then it will basically allow that job to rejoin the ready queue. Okay? So now you have again 3 jobs, and you can pick whichever one you want to run next. In that case, you would have picked the shortest job. So the job that was interrupted, because it rejoined, it has actually interrupted some other job in the middle of its time slice and rejoined the queue and got into run. Just because it happened to be the shortest job. If it was longer, it would have happened. Yes, question.
If something like that happens, if I/O happens after 0.5 seconds, when it goes back into the ready queue, does it get a whole new time slice, or does it just get like half a time slice?
The question is, if you think that you do I/O in the middle of a time slice and you rejoin, will you get your full time slice or not? Every time you start, you get a full time slice. It doesn't matter what happened previously. Whether you used your time slice or you did not use it is not material. When you get to run, you get a full time slice. Okay? Yes.
My question is for SRTF. If 2 jobs have the same length, how is it?
Okay, good point. The point is, if 2 jobs have the same length, what are you going to do? Okay? So in this case, there is no way to pick between the job. You can use any tie-breaking rule. You can just pick at random. Pick the job with the lower process ID. Doesn't matter what you pick. There is no way to pick one. So you just pick using some tie-breaking rule. Okay? So you have to implement some tiebreaker in the OS kernel saying this is what happens if jobs are the same length. This is the criteria. It's an arbitrary criteria. There's no right answer. Okay? Any other questions? Okay. So we will look at the next policy for a little while, and then we'll continue that next time. Okay, so we have now looked at 3 policies. First come, first serve, shortest job round robin, and shortest job first, and it's preemptive counterpart, which is shortest remaining time first. Okay? Now, there are some good things about shortest job first. Okay? It has no waiting times. Okay? That's a good thing because if you are interactive in nature, if you have any mouse clicks or any input, you will actually get to run quickly because the wait times are lower. But I said it's impractical because it requires knowledge of job lengths. Okay? So one question you should ask is, can I somehow approximate the behavior of shortest job first, which is try to get that good waiting time behavior, but without the limitations. Okay? It is not practical to ask about job lengths. So how is it possible to somehow come up with a policy that looks like shortest job first, but does not need any job length information? Okay? If you could do that, then you have a practical variant of shortest job first. Okay? Once you could actually implement and get some of those properties. Okay? The next policy we are going to look at is called multi-level feedback queue. Okay? That's basically an acronym for this policy, is MLFQ. Okay? This policy does exactly that. It tries to overcome the prediction problem of shortest job first. Okay, the question is, how are you going to do this? Okay. So the approximation you make in shortest in MLFQ is you assume that you actually need to know the future. The future is the job length, okay, but you don't know the future. Okay. But what you do know is the past. Okay. What the job has done so far is known. What the job is going to do in the future, how much time it will need is not known. You can't figure out the future, but certainly you know what's happened in the past. Okay? So what if you assume that the behavior of the job in the near future is going to be similar to its behavior in the near past? Okay? The recent behavior of the job in the past is going to look like what the job is going to do in the future. Okay? This is in general a good assumption because if you are sitting in a for loop, for example, computing, you are likely to do that for some more period of time. Or if you are doing some I/O, you are reading something from a file, you might read some more data from the file. Okay? So most programs actually behave similarly over some periods of time. Okay? So we are going to use past as a predictor of the future. It is not going to be a perfect predictor, okay? But it's always going to be an approximation, and it's going to be a reasonable one. Okay? So based on this observation, we'll come up with this new policy called MLFQ. Okay? But we are going to do that next time because we run out of time. So we'll have this discussion on Thursday.